Hello everyone, welcome to the Electronics with Bill channel. I'm a retired engineer, electrical engineer, many years, and I also taught UTA, Electronics, University of Texas Arlington for 5 or 6 years. And I'm not doing that now, so I thought I'd try doing some YouTube videos. Maybe you all could benefit from them. And for today's video, I'd like to talk about troubleshooting your circuits. If you build something in lab or at home and it doesn't work, what would you do? And so I had a couple of amplifier examples for today's video. What tools might you need to do this kind of troubleshooting? Well, the DC voltmeter DVM, really probably the most useful tool, a DVM, and an oscilloscope. Also, you can't really measure gains very well on an amplifier without an oscilloscope. Certainly would be hard to do with a DVM. So we're getting an oscilloscope and a DVM, and I'd like to start with a little video on how to set up an oscilloscope, or you really to be sure your oscilloscope is set up before you start doing measurements. And because, especially if you're going to measure gain, you need to make sure both of the channels on your oscilloscope are set up so you can, so that if you had the same input on both channels, you would see the same waveform on the screen. Otherwise, you really can't use an oscilloscope to compare the input and the output of an amplifier and have it mean anything. So for the following video, the scope that you see will have both of its channels connected to a waveform generator. So both channels have the same input. So on that note, let's get started with the video. A little video I took with my phone on oscilloscope setup.
Hello everyone. We're looking at a Keysight DSOX1102G digital storage oscilloscope. It's a pretty nice little machine, I would say. It has a built-in waveform generator, and the waveform generator right now, if you push the waveform generator button here, is set for a sine, 1 kilohertz frequency, 100 millivolts peak to peak, 200 millivolt offset. I put an offset on it. Most of the time you won't have an offset on it, but I put one on it just for demonstration purposes. All right, now, what do you have on the screen? Well, we have our channel 1 turned on. Channel 1 is turned on. You see the 1 is lit up there. The 2 is not turned on. Channel 2 is not turned on. So we have channel 1 only. And we see on the screen at the upper left-hand corner, very upper left-hand corner up here, 50 millivolts per division. And these are the divisions, vertical divisions here on the screen. There's 8 of them. So every one of those divisions is 50 millivolts. We have 2 divisions showing, and that would be 100 millivolts, which is what the waveform generator says, and that's good. You want that to match. You want your wave-gen output to match what you see on your oscilloscope, or something's wrong with something. Now, what about the offset? Well, the 0 is right here. Let me put my finger on 0 is right there, that little yellow mark. If you don't believe that, you can unplug the channel 1 input. I'll do that. Let's unplug the channel 1 input. And you see where the trace goes. That's where 0 is, of course. And so our trace jumped up 1, 2, 3, 4 divisions, which 50 millivolts per division matches the 200 millivolt offset that we had on the wave-gen output. So now you see we have the DC, and we have the DC content is 200 millivolts, and the AC content is 100 millivolts peak to peak at 1 kilohertz. Now, how do you change the vertical gain? There's this knob right here, vertical gain setting, and when I change that, I can change the how many divisions the waveform fills, and of course, unfortunately, it jumps up and down because of the DC offset when I try to change my vertical gain. So that's how you adjust the vertical gain, is with this knob here. What about this knob up here? That is the time base. The time base determines how fast or how many cycles of the waveform you have showing on the screen. And how would you set that? Well, since we have a 1 kilohertz sine wave, and the period of 1 kilohertz is 1 millisecond, if I wanted 2 full cycles showing on the screen, as we have now, 2 full cycles, that means we've got 2 milliseconds on the screen, and 10 divisions. Across this way, there's 10 divisions, so each division would be 2/10 of a millisecond. And glory be, right here we have 200 microseconds per division, 0.2 millisecond per division, times 10 is 2 milliseconds showing on the screen. All right, now let's turn on the other channel, the green channel, and it's also 50 millivolts per division, so it ends up, depending on how you adjust the position control, right on top of the yellow trace, and the 0 for the green trace is right on top of the 0 for the yellow trace, so that's good. Now, let's talk about coupling briefly. The coupling right now is set for DC. See that right there, DC coupling. All right, that means the DC and the AC, the offset is passed through to the vertical amplifier. And so if I, suppose I needed to look at the ripple on a 48 volt supply, ripple is 25, 50 millivolts peak to peak on a 48 volt supply. Well, if I turn up the vertical gain enough, I can see the ripple. The trace will be so high off the top of the screen, I won't be able to pull it down with the position control. And every time I change the gain, the trace is going to jump all over the place. Let me show you again. You change the vertical gain, the trace goes up and down. Now it's off the top of the screen, the yellow trace is. Okay, so you know, that's what AC coupling is for, and it sure is nice. Well, here's what we're going to do. We're going to take and change the coupling to AC. And that was for the green trace, and now it's for the yellow trace. Let's change the coupling to AC. And now, both traces, let's bring these traces up here. And this jittering that we see is not anything wrong with anything. It's the oscilloscope triggering. You see, I'm adjusting the trigger level now. And if I don't have the trigger level adjusted right, the scope does that. And if I get the triggering adjusted right, the scope doesn't do that. Now I want you to observe that we have AC coupling on both green and yellow, and I can turn the vertical gain up and down, and the trace does not jump off the top of the screen, which is very nice. All right, so I have a little problem with the triggering on the scope, but again, that is not the fault of your circuit. If you see that kind of jittering like that, it's just the scope is starting the picture at different places every time it redraws it, and it causes that jittering. Sometimes you just have to stop the waveform. So now I think we've talked about how to adjust the vertical gain. That determines how high the picture is this way, up and down, and how to adjust the time base, which determines how wide the trace is back and forth horizontally. And I think the important thing is that you have both channels working and they both read the same thing, so that you can use it to compare the input and the output of your circuit. You have confidence that both channels would show you the same thing if you had the same thing there. Now, obviously, if you're looking at an amplifier that's got some gain, you're probably going to want to adjust the output channel's gain to be less, so that the trace won't be so big it'll be off the screen. If you have a lot of gain, if the yellow was the input and the green was the output, you want to turn down the gain of the green channel so that it wouldn't be off the screen. So when you add gain in the block you're measuring. Anyhow, that's just basic oscilloscope setup. That's all there is.
Hello, everyone. I thought we'd take a look at a circuit that I've seen folks have some trouble with getting it to work. It's a simple amplifier circuit built with a bipolar junction transistor. In this case, it'd probably be a 2N3904 would be the device. Not that it matters. I'll write that down here, 2N3904. And then we've got a 10 volt supply, a source, a signal source here, AC signal source. I've got an oscilloscope, two channels, one channel looking at the input from our source, and the other channel looking at the output. We don't have another load here. The load for this amplifier is effectively the collector resistor. You might have, in some cases, a capacitor coupled to another load or whatever, but for this purpose, for this right here, our load is the collector resistor, and our output is right there on the collector. All right, and these are supposed to represent scope probes here. Uh, the and the ground clip on the scope probe connected to circuit ground. So we have a DVM here. The common lead on the DVM is connected to our circuit ground with an alligator clip or whatever, frees up a hand, and then we can poke around and touch things with this. I chose this circuit for troubleshooting because the theory is always check the DC first. And in this circuit right here, if your DC is right, almost you almost have to be operational. It's really hard for the DC to be right and not have not have the circuit work. So how would you where would you start here? Well, very first thing always start with is touch the supply lead right at the power supply and verify that you get whatever the supply voltage is supposed to be set to. Hopefully, maybe before you ever connected this up, you maybe turn the supply on with this lead disconnected to see that the supply is not going to come up to 60 volts or something ornery like that. Uh, uh, Maybe you don't have to do that depending on your power supply, and that the current limit is set to something reasonable, maybe a tenth of an amp or so, so that if you accidentally short something, you don't burn up things. Well, so that's just good practice. You don't always have to, and usually you can get away with it if you don't, but it's a good thing to do. We had some power supplies in the lab at one time that you turn them on and they'll come up to whatever the last person left it at, and you don't know that until you turn the power supply on. So just good practice. So we're going to probe around and touch things and see what we get. But what should we get? That's the question. So let's just do some calculations. How do you analyze this circuit? That's probably probably a good thing to do. And by the way, this is R2 is 1K. This is 1K, and this is 6800. Okay, the resistor values. So let's just do some calculations here. What is VB? What's the voltage on the base? I'm going to use the voltage divider rule. So VB, voltage on the base, is going to equal to 10, that's the supply voltage, times, and then this resistor divided by the sum of those two resistors. That's our voltage divider rule. So that's going to be 1K divided by, and then the sum of those two, 1K and 6800 is 7800. So that's 7800. Okay, and what is that equal to? 1.28 volts. All right. And then what should VE be? If that's the case, VE should be equal to, this is an NPN BJT, so the emitter should be 7/10 of a volt less than the base at room temperature. So VE should be 1.28 minus 0.7. So that's going to equal to minus 0.58. And then IE, the emitter current by Ohm's law, is going to equal to this voltage here divided by the resistor value. So that's 12.4 milliamps. And that's equal to 0.58 divided by 47, equal 12.4 milliamps. And then, assuming the collector current and the emitter current are almost identical, and that's a really good approximation, then our collector voltage is going to be 10 minus 12.4 milliamps times 330 ohms. So VC, we're going to assume this is also approximately equal to IC, collector current. And so VC is going to equal to 10 minus 12.4 milliamps times 330 ohms. All right, so doing the math on that, that's going to equal to 5.91 volts. All right, so Now we've got some voltages, and if we were to measure around, we'd probably find not exactly these voltages, but pretty close to these voltages. The VBE won't be exactly 0.7 volts. You can be sure of that. The collector current's a tiny bit less than the emitter current, but not a lot. So this is a pretty good first place to start for voltages. Now, if these voltages are all correct, you should be good to go. So turn on your AC source if it's not already on, and maybe 100 millivolts peak to peak. For AC input, 100 millivolts PPK. Now, it doesn't matter if it's bigger than that as long as the amplifier doesn't clip. And it can be bigger than 100 millivolts peak to peak. Then V out should be the AC component of V out should be the gain. The gain of this circuit is going to be roughly this resistor, 330 ohms, divided by this resistor plus the little RE, which is about 2 ohms. We're running about 13 milliamps of collector current. So the gain is I didn't write that down, but the gain is going to be approximately negative 330 divided by 47 plus 2, which would equal to 6.73. So our V out AC here then would be 673 millivolts peak to peak. Yeah, 673 millivolts PPK, and invert it because this amplifier is an inverting amplifier. The gain is negative. I forgot to write that down up here. Negative 6.73. All right. Now you poke around and you measure things. What gets people in trouble here? Very often, put the device in backwards. Put the device in backwards. Try to use the collector for the emitter and the emitter for the collector. Your beta is horrible, and it won't bias upright. And it'll be really obvious to you when you do DC measurements something's wrong. So for these devices, the 2N3904s and the TO92 package, when the flat side's facing you, it's emitter-based collector left to right, but the data sheet tells you that. You don't have to remember that. And just make sure your device is in correct. When you measure voltage on the emitter-based and collector, touch the lead right on the device. Touch the lead of the device. That way you be sure you're actually measuring what the device is seeing. Sometimes the leads of the devices don't make contact in the whiteboard. So if you have an intermittent connection, that'll be confusing. But very common to get the device turned around. Another thing that's really common is that these two resistors will get flipped. You'll put them in the wrong place, interchange them, and of course that causes the device to saturate. So you'll have a real low collector voltage. But anyway, I think this technique right here, you can use this not just on some little circuit that you built in lab, but the circuits that you see on other people's product, and it'll give you an idea what's going on. Again, the DC pretty much tells you, if you have a wrong resistor value, or use a PNP device instead of an NPN device, or you've got the device inverted, the DC tells. Hey, I want to say a little more about this circuit in terms of what you do if something is not right. One thing you can do, if it's possible and easy, is pull the device up. Just take the device out and then check the voltage on the base. Voltage on the base should be exact per the voltage divider when you unplug device. If you plug the device back in again correctly, not inverse, then the voltage shouldn't change very much. But if you plug the device in backwards, then this voltage will change when you plug the device in because the beta is very low in the inverse mode. All right, so if this voltage is right, then this voltage is going to be right unless your device is just totally destroyed. Unlikely. Okay, and then this voltage will be right. What about this voltage? Well, if this voltage is wrong, let's look at the equation for what determines this voltage. The equation for what determines the collector voltage is this guy right here. Now, there are two knobs that you've got. One is the collector resistor, and the other is the current. What sets the current? The emitter resistor sets the current. And what sets this resistor? Well, that's that resistor. So just an idea of if this voltage isn't right, it could be either, like for instance, if this voltage on the collector here is too low, then that suggests either too much emitter current because this resistor is too small, or too large of an emitter resistor, collector resistor. Too large of a collector resistor would cause this voltage to be low. Just wanted to say that. All right. Now, again, the device is usually not bad, but if you think it is, unplug it and use your ohm meter. Put your DVM in the diode mode and just check the emitter base junction and the collector base junction. They should be diodes. That is conductive in one direction and not in the other direction. And then the collector emitter junction should be open both directions. So if it flunks those tests, your device is indeed bad. Also, if you see this voltage here as what was it supposed to be, 1.3 volts, and this voltage is 0, if you see more than 0.7 of a volt across the emitter base junction, well, that means it's been blown up. But in most cases, you find that a circuit that's that did used to work and now doesn't, well, that could easily be a device failure. But if it's a circuit you're just putting together, and most likely it's some resistor value errors that are causing your problem. So I just wanted to say that. And lastly, maybe if your AC stuff is not working right, make sure your frequency is not 10 megahertz or whatever. You want to be down in kilohertz. Start out at a kilohertz. Get it debugged at a kilohertz before you turn up your frequency. Go looking for trouble, so to speak. All right, so that's it for this circuit. I'd like to go into another circuit with an op amp that's a little bit pretty simple, but it causes some issues. Hey everyone, here's another circuit that probably can talk about here a little bit. Just a brief discussion here. It's an op amp inverting amplifier. Gain should be -10 based on the ratio of these two resistors. Dual supply. Sometimes that causes people issues because of the dual supply. Oscilloscope monitoring the input on channel 1 and what's coming out on channel 2. And maybe a DVM for troubleshooting. The one leg of the DVM grounded with an alligator clip or something, so you don't have to use your hand. That way you only need one hand to work this probe for troubleshooting. Of course, the very first thing you're going to do is check the DC voltages. But you get your supplies set properly, and you get the current limit set properly, and then you turn the power on and verify that neither supply is in current limit. And then with a voltmeter, you might check this voltage right here, right at the supply. Should be +5 or whatever the supply is supposed to be. This should be -5 or whatever the supply is supposed to be. And this should be 0 because this should be the same potential as that because they're connected together. Now, if this potential is not 0, then that means that you didn't connect this up to your circuit ground. And that's a common thing that happens. So why you check right at the supply, and if the supply voltages aren't right at the supply, then they're not going to be right anywhere else. So if you find that this voltage is not 0, then fix that. Okay, don't throw anything away or start debugging your circuit, however, until you see your DVM work. Your DVM might not be turned on, or maybe something wrong with it. So make sure you see some life from this on something before you start tearing your circuit apart. Use a flashlight battery if you have to, just something to check it out, see if it's working. You don't see any signs of life when you start poking around over here on the supply. If you do have the supply voltages correct right at the supply, then come over to your op amp and touch the pin 8, if that's the positive supply pin. Touch the leg on the IC, because there's too many cases of op amps not plugged all the way in, or a lead folded under the package rather than being plugged in. So check it on pin 8 and pin 4. Make sure that you actually have these +5 and -5 if that's what it's supposed to be. And of course, pin 3 here, this should be ground. And then if all of those voltages are correct, then you can look at this. That should be virtual ground, so that should be darn near 0. No matter what the input and the output are, this should be darn near 0. So those would be the DC voltage checks that you can make before you start worrying about anything else. Okay. If you find out that your supply is in current limit, one of your power supplies in current limit, and your current limit is set, maybe 0.1 amp or something like that, then of course these voltages won't read correct if a supply is in current limit. And so why is it in the current limit? Well, one of the things that I've seen mistakes is that because of the data sheet that shows, for the LM358 at least, shows this pin 4, as ground. They label it as ground in the data sheet. And that would be the case for a single supply op amp circuit. You would ground this if you only had one supply. Then this would be your positive supply, and this would be ground for a single supply application. However, this is a dual supply application, so this is your negative supply. If you also connect it to ground, in other words, if I connect this pin here to both the negative supply and to ground, I've effectively shorted out this supply, so this supply will be in current limit. Just an observation that I have seen. Now, if all of the DC voltages are right, you can start paying attention to what you're doing AC-wise. And of course, your scope should tell you what you have on the input, and that should be whatever your signal source is set for. Maybe 100 millivolts peak to peak, let's say. Shouldn't have it be too large, because you would expect this to clip. 4 volts peak to peak or so. I'm sorry, 8 volts peak to peak is about all you're going to get here with supplies set here. So with a gain of 10 here, you can't have too much input before it's going to clip. So pay attention to that. And then, so if this is 100 millivolts peak to peak, this should be about 1 volt peak to peak, and the output should be inverted with respect to the input. So the output should be inverted with respect to the input, flipped over. If your output is inverted with respect to the input, your amplifier is working. There's no mistake you can make that will cause the output to be inverted with respect to the input for a circuit that simple, without having the amplifier function. Now, if the output's inverted with respect to the input, you're almost there, and then the only thing is the resistor ratio. I've seen a lot of cases of just of 247Ks or 4.7Ks or 470 ohm resistor for one of these two instead of 4.7K. Just that kind of thing that would cause the output to the ratio, the gain, to be wrong. But the circuit's working, but the gain's wrong. So it almost has to be a resistor ratio thing here. If the output of the op amp appears to be just huge, in other words, it's banging rails from one supply rail to the other, even for tiny input, that kind of suggests this resistor may not be connected. And I would suggest putting this feedback resistor right at the op amp, just between pins 1, which is the output usually, pin 2 is the inverting input. Let's put the feedback resistor right between those 2 pins, right on your whiteboard, right up close to the op amp. And if you want to run a jumper or something like that over to some other node from pin 1, that's fine, but put the feedback resistor right at the op amp. Okay, so lastly, if you're having inverting summer or something like that, and just disconnect to all of the inputs except 1, and troubleshoot your inverting summer with just 1 input, and then when you get that to work, you can connect up the other 2 inputs, and You make your circuit simpler when you troubleshoot it. Just a suggestion on that. So fairly simple circuit, but because it has a dual supply, it causes people issues sometimes, and that's just why I put this example in there. Um, and that's it for this video. Hello again. Thought we might take a look at a little more advanced, for people that are interested in a little more advanced study of this circuit. We look at bandwidth a little bit. So what would you expect for the upper and lower 3 dB frequencies for this circuit here, a simple amplifier? Well, the lower 3 dB frequency is set by this capacitor, 10 microfarads, and the input resistance of the amplifier. The input resistance of the amplifier is this 1K resistor in parallel with that 6800, and then in parallel with the input resistance looking into the base of the device here, which is the beta times the emitter resistor pretty effectively. So all that works out to be about 800 ohms, depending on what you assume for the beta of the device, around 800 ohms. So 800 ohms shunt and 10 microfarads in series is going to give you around an 18 hertz corner frequency, and on the low side, 18.2 hertz. And that's what LT Spice says. The low frequency corner is 18.2 hertz. By the way, the gain LT Spice will give you is 15.9 dB. That was measured with a source here with a 50 ohm resistor in series with it. And because of the 50 ohm resistor, this number is about a half a dB less than the 6.73 numeric number we calculated previously in the video. So in other words, you had some drop across the 50 ohm resistor, which caused the input voltage at this node to be a little bit less than the 1 volt that was assumed in the sinusoidal in the AC analysis for LT Spice. So anyway, the gain's about 16.5 dB. If you correct for the half dB across the 50 ohm resistor, the lower 3 dB frequency is 18.2 hertz. What about the upper 3 dB frequency? Well, there's nothing here in the schematic that we just looked at that would set the upper 3 dB frequency. It's all infinite bandwidth as far as any components shown are concerned. But of course, the device has some capacitors that limit the device model has some capacitors that limit the bandwidth to 69 megahertz for this amplifier. That's according to LT Spice, and that's with no parasitics whatsoever. Now, as you could imagine, there are some parasitics, and most particularly the whiteboard or solderless breadboard or whatever you wish to call it. So I have a cheapy solderless breadboard here, and I took a C meter. I don't know, hopefully you can see that. This is a simple solderless breadboard. I took a capacitance meter and I shoved a couple of resistor leads in there on adjacent rows, and just measured the capacitance between them with this little solderless breadboard floating, not connected, not sitting on any metal or anything. And I got 2.2 puff between two rows that are side by side. Less than that if you measure between two rows that are farther apart, maybe by half a puff if you measure between two rows that are several rows apart. So I guess that kind of made sense, a little more than I thought. And then I measured the capacitance from any given pin, doesn't matter which one, to this aluminum foil here that I'm setting the whiteboard on. And I got about 2 puff capacitance from any given pin to this aluminum foil. Now that aluminum foil, a lot of the solderless breadboards that people use have the metal backplates on them, and it's not connected to anything. It kind of float, which is kind of scary when you think about it. But especially since the backplate's connected to every pin with a 2 puff capacitor. So if you draw the schematic model of what we just said, the capacitance, here's the model that you have. We have from a pin in row N, we'll call this row N, and then this is row N plus 1. We have 2.2 puff capacitance measured here, but we know we have 2 puff to the aluminum foil, 2 puff here, and 2 puff here, and this is kind of floating, or maybe some capacitance to earth ground. Just, I don't know what that capacitance is, but I just, for the sake of argument, presumed that this was floating. And then you can kind of see, I think, that 2-puff in series with 2-puff gives you 1-puff, and that it could be that you actually have something on the order of about 1.2-puff actually between these two rows, such that 1.2-puff plus this 1-puff gives you 2.2-puff. So I wouldn't go to the bank with that, but I just thought, well, let's just see what happens if we put 1.2-puff of extra collector-based capacitance in this device, because collector-based capacitance is not good. And so if we added 1.2-puff here, right here, to kind of sort of model the capacitance between the row the collector plugs into and the row the base plugs into, 1.2-puff there, and then ran this sim again, I got some degradation. The 3 dB bandwidth was 52.5 meg instead of 69 meg. So a rather significant degradation in bandwidth on the high side. Of course, no change on the low side, as you would expect. So 52.5 meg with a 1.2-puff collector-based coupling cap. Now, if students in lab measure this and they don't get anywhere near 50 meg bandwidth on these, they're lucky to get 10 meg or 5 meg bandwidth. So what else is going on? And the answer is, and this may come as a surprise to you, the capacitance of your measurement setup. So if you have a oscilloscope with a 15-puff, oscilloscope has around a 1 meg in parallel with 15-puff, I believe, as the input. This is 1 meg, parallel 15-puff, looking in there. And then you put 3 feet of coax. And folks like to use those like 50 ohm, like RG58 with alligator clips on the end. So 3 feet of that gives you, this is around 32 puff per foot. So the capacitance looking in here at the end with the alligator clip, you got the alligator clip here and one for the ground. Capacitance looking in here is going to be about 96 plus 15, let's say 110, approximately 110 picofarads of capacitance, and then of course that's in parallel with the 1 meg for the scope. 1 meg doesn't even matter. That's 1 meg's totally out of the picture. So now if we put 110 picofarads in parallel with the collector resistor, or from the collector to ground, either way, it's the same thing, because the supply is ground for AC purposes. So now, what do we get for a bandwidth? 4.1 megahertz. 4.1 megahertz if I add 110 puff shunt C on the output. And now, we finally get to the punchline here. If we take, and instead of using the RG58 with the alligator clips, if we use a real scope probe in the 10x mode, which has a 10.5 puff capacitance when it's in the 10x mode, then if I take out the 110 puff cap in parallel with the collector resistor and put in a 10.5 puff capacitor, my bandwidth increases to 25.7 megahertz. Still severely degraded, but much, much better than if you just use the scope probe in the 1x mode, or worse yet, RG58. So now I think maybe you can understand why we have 10x scope probes. And it's not so that we can have 100 volts per division, we can measure high voltages. It's so that you can reduce the capacitance to something that's almost tolerable. And 10 puff is not very good, but it's a whole lot better than 110 puff. That's why we have 10x scope probes. Reduces the capacitance. If you're doing audio measurements, maybe you don't care, but anything else, you do. Now, I wanted to say, that's all I had on this subject with the bandwidth. I wanted to just say, if you are actually working on something else, like your television set or something like that, what can you do? what can you do? You don't know what you're looking at. If you're working on your TV set, you don't know what you're looking at unless you know participated in the design or something like that. You don't know for sure what the circuits are supposed to do. You don't know what the schematic is. So how can you possibly troubleshoot? Well, you look for visual inspection. Visual inspection is probably very important because very often uh, uh, you can find things without even doing any electronic troubleshooting. So visual inspection is the most important thing. What are you looking for? What are you looking for? Leaky capacitors or bulged capacitors. Uh, if their bulbs are leaky, that's bad. Anything burned, um, uh, clean the circuit board up. Clean the dust off it so you can see better. Look at things under a microscope. Solder fatigue. Any components that are like a potentiometer or something that's on the edge of the board that with a shaft that comes through to the outside world. When people work that, they might put some stress on the solder joints, and the solder joints where that part was soldered to the board will fatigue, and then you'll have little cracks in the solder joint, and they won't be making connections. So inspect questionable solder joints with a magnifying glass. So just and then resolder them if you think that something might be bad. That's a pretty significant failure mechanism for consumer electronics, solder fatigue, for things that uh, temperature cycling too can be bad. So look for that, and then fuse. If there's a fuse on the where the power comes into the board, check that out. Always, sometimes they just blow from just you get so many cycles, and then the element will break, or here's a little transient, maybe from a lightning storm or something like that. Not maybe enough to blow up any electronics, but it'll take the fuse out. And so it's worth your while to look for your fuse. You can ohm it out with an ohm meter. Google, just Google it. A lot of the stuff you get on Google is just garbage, but you might get some hints from someone that's actually fixed the same problem you have. Uh, I'll just say try Google, but that's question mark. You waste a lot of time, wading through stuff that's not even worth anything. But that's about all you can do if you're working on your television set. Uh, try to reverse engineer. Used to be maybe you could hold the board up to the light, up to a bright light, and kind of see where the traces were. While you're looking at one side, you can see where the traces were on the other side, and try to figure out what was connected to what. And judicious use of an ohm meter, you can figure out what connects to what. But man, that is so time consuming. And then if you do kind of map out the schematic, you still don't know exactly what the circuit's supposed to do. So oh my goodness, is it ever hard to troubleshoot stuff these days? But anyhow, that's just some suggestions for those that want to go a little bit farther than the real basic stuff. And that's I think that'll be it for this video. Well, I hope you were able to get something from this video. And if so, or if not, please leave me a comment. I'd appreciate even the negative comments. Help me do what you can benefit from. Uh, so on that note, I'm gonna end the video, and we'll see you on the next one.